and Mark Tritchler from Kima Limited to enlighten us as to what smart grids are and how smart mathematics can help meet the associated challenges.
Thank you very much, Chris. Can you all hear me okay at the back? Yep, good, thank you. Thanks for that introduction, Chris. I will do my very best to say something useful about smart grids. I'm not going to go into huge swathes of detail. I guess this will lead us nicely into the discussions this afternoon, and obviously I'll be around and we can take the discussions forward. So I see this as being a taster. You may already know a lot of it, you may not. I'm not familiar with you as an audience, so let's see how we go. I should also say that I'm not a mathematician, so there's no maths in this presentation. Okay, so the first thing I want to do very, very briefly is just say a little bit about Kima. I noticed that Andrew didn't have to introduce National Grid in his talk, which is fine, but you may not know Kima, so I'll say one or two words about Kima. I'll give you a bit of an overview of the network, the electricity network, particularly from a GB perspective. And I'll also talk about some of the dimension issues. I'm going to focus more on distribution networks than transmission network. I know obviously Andrew spoke. You've had a presentation from Chris Murray at National Grid as well yesterday. So you've had very much probably a transmission-oriented view of the situation. Hopefully I'll be able to add in some of the distribution network view of the situation. A little bit of an overview about, well, what are smart grids, what could they be, is probably a more accurate way of saying it. And I'll pick up on a couple of examples. An example of a future network scenario related to distribution networks and what kind of challenges that will provide to the distribution companies. And I'll also talk about an example smart grid architecture and the components that might exist within that architecture and the sort of challenges that will present to the industry as well. There we go. Just a bit of headline data about Kima. We're a global organisation. We've been around a long time, as the slide says. We're not a huge company, 1,600 odd employees, but we do have a worldwide presence, and we're fairly healthy financially as well. In terms of our ownership, we are actually we're based in Holland, and we are owned by the Dutch utilities. We were originally started way back in 1927 as a kind of research and development and test house for the Dutch utilities. And that is something that we still continue to do insofar as testing of transformers, high voltage cables, that kind of thing, and certification. But we also do a lot of consulting related work in the industry. So there's really two main business lines for Kima. The consulting part of the business, where we focus more on the electricity industry than anything else. But we also work within the gas industry and also within the water utilities as well. And we work very closely with transmission and distribution companies, particularly both gas and electricity, providing both business and technical consulting. We also work in the generation industry as well on various forms of generation. And in general terms, on the utility market, we provide assistance to governments and regulators and so on in terms of setting up liberalised markets, both designing them and regulating them as well. And I mentioned before the Kima technical and operational services part of the business that focuses on things like testing and condition monitoring and so on. So, moving on to the electricity grid as it stands at the moment. This is a picture which no doubt you're all pretty familiar with, but I'll just walk through it. And this is based obviously on what we have in place at the moment. Typically, we have large centralized sources of generation, and we have a transmission network with high voltage substations which is responsible for moving that energy out towards the consumers. Past the high voltage substations, we then go into a network of medium voltage and low voltage substations on the way to people's houses and to business premises and so on. And the key thing, I think, to focus on in terms of the current electricity grid is the flow of electricity is outward, typically from the central sources of generation. Now, obviously, Andrew's talking about demand forecasting from a transmission perspective is focused on the national demand, if you like, broken down into zones, sure, but in general terms, the national demand against the national forms of generation. Now, obviously, National Grid has the problem of being able to manage the power flows between the central sources of generation and the high voltage substations, but not beyond that. That's a matter for the distribution companies. But because the flow of electricity is that way, it's something that the distribution companies really, up until now, haven't had to pay too much attention to. What they've done is they've designed their networks to cope with the maximum demand that they would expect to see, and they don't really do a great deal in terms of managing the flow of electricity around their own networks because they haven't had to. So just to talk briefly about the distribution network operators in GB, well, Northern Ireland is also shown there, but essentially the country is broken up into 14 different distribution regions, and in each region there is a monopoly provider of electricity distribution infrastructure and services, and the ownership of those organisations is different in that it's not 14 different owners. There are 7 companies, including Northern Ireland, who own the 14 distribution networks. So typically, what are the attributes of a distribution network? Now, this is not accurate across all of the distribution networks in GB, but this is just a representative sample. And remember that this is really from the grid supply point downwards. So this is where the responsibility of National Grid ends and where the responsibility of the distribution company starts. So a typical distribution company will have something like 30 grid supply points where we're transforming down to, say, 33 kV, down to 11 kV as well. It will have something like 700 primary substations, and feeding off of that, there'll be something like 4,000 11 kV circuits. Of course, 11 kV, 11,000 volts, is not what we feed into people's homes and premises, so we need to step that down again to typically 240 volts, and we do that through something like 100,000 or thereabouts local transformers. And that gets us down to having something like 150,000 240 volt circuits, and typically something like 5 million connected customers on each distribution network operator's territory. In terms of length of network, that's something like 130,000 kilometres, 3 times around the world, and that's for one distribution network operator. If we compare that to National Grid as the Great Britain system operator, they're operating something like 600 sites, 2,000 odd buses, 22,000 switches, and about 1,500 lines. If we compare transmission to distribution, and this is just to give you an idea of the scale of the distribution networks, all of National Grid's lines and transformers that I've just mentioned, the say 1,500 lines and 1,500 transformers, are all fully metered with full status indications to the control centre. Whereas if we compare that to the 7 DNO companies, high voltage and low voltage only, we've got something like 1 million HV and LV lines, we've got something like 670,000 transformers, and we've got really very limited status and metering information. So the distribution companies don't really know, down to the lowest voltage level, what's happening on their network with any great degree of accuracy. And then, of course, in the past, that's not really been too much of a problem because of the one-way flow of electricity. Whereas if we now move to the smart grid idea, and I won't go into too much detail as to, well, why smart grids. We could maybe talk about that a bit later. But obviously, in summary, the move towards low carbon, the low carbon transition, what we're expecting to see is large-scale electrification of heat, large-scale electrification of transport. We're also having to integrate different forms of generation, more and more being integrated onto the network at distribution levels rather than transmission levels. And in order to do that, one of the options that we have is to implement a smart grid. I guess we have two options really. One of the options would be put lots more copper in the ground and up on transmission towers or distribution lines. Or alternatively, let's have a look at smart grids and see if we can use that to reduce the amount of copper that we have to add to the system. Inevitably, we are going to have to add more copper, by the way. There's no question about that. But I guess the challenge is getting to a position where the amount of copper that we have to add is optimized, and we use smart grids to reduce the cost or to come to an optimal cost. So what are smart grids? Well, a bit of a mess, really. We can envisage, and of course this is all looking into the future. We can't really say we have any of these things fully implemented yet. We have bits and pieces of these things implemented, but we don't have them implemented yet in a kind of holistic, complete way. But what we can expect to see, of course, are the continuation of centralized power plants, although perhaps less than we've currently got at the moment. And we will start to see much more, as I said before, in terms of dispersed sources of generation. We could have micro turbines, we could have energy storage sitting on the system at various voltage levels. We've got wind turbines on the system, again coming on at both transmission and distribution levels. We've got virtual power plants which are taking the output from micro turbines and various other small sources of energy and aggregating them up in order to provide a service to the market. And as I said before as well, we've obviously got the integration of these new things that are going to come along, like electric vehicles. There's also new technologies, for example, heat pumps, which have a demand, obviously. So the whole dynamic of the system changes, and it will have to become, the distribution system will have to become a lot more dynamic. Now this is the only formula I'm going to put up there. E equals mc squared, and I'm not going to claim credit for this one. I heard it yesterday, and I have to say I thought it was absolutely fantastic. And that is that energy in this world requires measurement, control, and communications. And I thank Peter Crossley at the University of Manchester for giving me that one yesterday. But I think this is the key challenge that we face. In order to facilitate all of this, we've got to be able to measure it, we've got to be able to control it, and we've got to be able to communicate between all these different devices and components that will sit on this grid in order to make them work together. So, excuse me. If we move on now to one of the examples in a future network scenario. The diagram is a little bit simplistic in that we've just shown 4 houses here, but of course in the smart grid world, those houses will not necessarily just be consumers of energy, they could also be producers of energy. They could have some kind of micro generation, They could have a combined heat and power plant there. They could have photovoltaic cells on the roof, etc. They could be a source of generation. They could also have an electric vehicle sitting there fully charged, which could be used as storage to feed into the system, as well as being a demand on the system. So the diagram is a little bit simplified in that it doesn't show all of that detail, but imagine it's there. Now, in the old world, the distribution network company will have designed the network to cope with the maximum demand that they expect to see from those four demands, because in the old world they would only be demands. So that the flow would go that way, and as long as the network company put in a big enough cable, a well enough rated cable, and the demand didn't change too much here on the end of the network, then everything would be fine. But what we perhaps have in the future is where those houses, let's call them that, have demand profiles which might be changing very, very rapidly. So those demand profiles might now have to include ground source heat pumps. They might have to include electric vehicle charging. So the demand will increase and the profile of that demand will change. But also, as I said, those four houses could also have some form of generation in them. And this would mean that they would be feeding back into the network. Now, bear in mind, of course, that under the current situation, the distribution company has no visibility of what's happening on that cable. So that's the first problem. But the distribution company in the future will have to be able to cope with all of the whole dynamic situation on that segment of the network. So the example is that an overload occurs on that particular leg, either because of import or export power flows, so either demand or local generation, created by those three houses here. Obviously this one is not part of the equation. So there are a few questions that the distribution company will have to ask itself. First of all, how could the distribution company have perhaps predicted this? Does it have any tools in its toolbox at the moment to actually predict that this overload could have happened and actually do anything to prevent it? The current answer is no. But in the future, that answer could be, well, the simple answer, as I mentioned earlier, is install bigger cables, but that's a rather expensive answer. But it may be able to use tools or methods such as demand forecasting down at the distribution level in order to try and preempt what might happen on that cable. It might be able to use tools like distribution state estimation, which again is not particularly common in distribution networks at the moment, but it is in transmission networks, where algorithms are used to identify what the power flows are on the network at points that are not being directly measured. And perhaps also using the predicted demand, it could actually use some preemptive controls to actually prevent the overload situation from occurring in the first place. So on the assumption that it could have control of the export sources that now exist in those three houses, then yes, perhaps it could do that. And equally well, if there is localized energy storage there, it could perhaps use that to adjust the flows on the network to prevent the line from going into overload in the first place. The next level down is, well, if they can't predict it, or even if they can predict it, there is still a question of, well, how do we actually, as a distribution company, have visibility of this problem? And with the national rollout of smart metering, which should start coming along soon, there is a possibility that smart metering in those houses could provide some information which could then be aggregated by the distribution company in order to identify when an overload is occurring. Equally well, the network company could install its own network monitoring devices to measure and identify when the problem is occurring. So having done all that, what can the distribution company actually do about it? Well, of course, the first answer again is the easy one. Well, it could have installed bigger cables in the first place, and the problem would subsequently go away. Alternatively, there's the prospect of demand-side management. So, could reactively, rather than proactively, could the distribution company actually prevent some demand from occurring? So, in other words, curtail a customer's demand down to the granular level of on a per home basis, or again, could it control the export sources within the home to prevent the exports from occurring, all in real time? So that's the scenario. Those are the kinds of questions that the distribution companies are starting to ask themselves, and those are some of the things that they see as potential solutions. But what kind of challenges do those potential solutions pose? Now, I've listed all of the ones that I could think of here. Some of them are purely commercial. Some of them are purely based on the relationship that the distribution company has with the customer. And for those of you that don't know, the current state in Great Britain is that actually the distribution company doesn't have a relationship with the customer. The customer buys his energy from an electricity supplier who's not really part of this situation at the moment. So, simply things like who should actually contact the customer, the distribution network operator or one of the suppliers, bearing in mind, of course, that each home could have a different supplier, so that the actual arrangements for communications could become very, very complex. We've got issues like electric vehicles providing a significant demand, but that demand is not necessarily location specific. That demand moves around. It's not fixed to the house. So how do we get better, given that we don't really have electric vehicles at the moment, but how do we forecast this? Can we come up with some models that allow us to forecast the demand from electric vehicles, which are based on the movement of electric vehicles, typical movement of electric vehicles during the course of the day? As I said earlier, we don't know what the demand profile will be really, because of these new sources of demand, electric vehicles and heat pumps, for example, and that demand profile will therefore be very different to what it is now. So how do we work out what it's going to be? The distribution network operator, and I've been very careful to call them the distribution network operator up till now, because that's essentially all they're doing. They're operating the network from the physical perspective of making sure it's available to supply energy to customers. But this organization will now need to have visibility right down to the granular level, and it must be able, well, you would imagine it will have to be able to respond in real time or near real time. And we would term that as becoming a distribution system operator, in the same way as National Grid is the transmission system operator. Again, back to some commercial issues of who would have the agreement with the customer for curtailing demand or export. On the assumption that the customer would want to be paid for being interrupted, how will this all be settled? Where do the calculations happen? Who works out who owes money to whom? But I think probably most important is if we work on the basis that in the future someone will be making decisions on demand and export down at this granular level, then how will we actually optimize those decisions? Because we've got a hierarchy of transmission and distribution. We've got National Grid who need to make certain decisions and optimize those decisions for the sake of the transmission network. And we've now got 14 distribution companies who are doing a similar or trying to solve a similar problem but at a much more granular level. How do those two interact with each other? Because I'm pretty sure they will need to interact. And I think this is an area where there is a huge amount of uncertainty about how that would work. So that's the example of just a typical future scenario, and hopefully that's raised some thoughts about, well, okay, what kind of challenges are the distribution companies going to face? I'll leave it to you guys to work out, well, where does maths come into all of that? I'm sure it will come into many, many places there, but not being a mathematician, it's not my place to say. If we have a look at the second part of what I was going to say with regards to the smart grid architecture and smart grid components, again, just to show this diagram, to show the various different components that will make up the smart grid system, let's call it that. You know, it will be a heterogeneous network, let's say, lots of different types of things on this architecture or on this network, all contributing in different ways to the achievement, if you like, of the smart grid. If we talk briefly, I'll not go through this list one by one, but again, this is just a brain dump list, essentially, of what we can currently see would be potential smart grid or potential components of the smart grid, both in the near term and also in the medium to longer term. So just to summarize, we've got lots of active devices on the network itself, measuring and potentially controlling at a very localized level, but also contributing up the hierarchy of control, if you like, in order to control the overall smart grid. We have lots of different forms of demand and sources which could be made smart. So we have electric vehicles which obviously will need to be charged up, but could that charging be made smart? Can the charging post make some intelligent decisions about when to charge the car? And those decisions could be based on prices. Those decisions could be based on a whole range of different tariffs that might be available from different sources. So the distribution company may offer a tariff for actually using some of the charge from the car or from the vehicle to support the network locally. But the customer will have to pay for charging his car. You'll have to pay a supplier, no doubt. So there's a very, very much more complex set of arrangements that will need to be put in place, both commercially and technically as well. But we will have more and more smart things in homes and in buildings, controlling lighting, controlling heating, perhaps even controlling industrial processes, all with the efforts of trying to, in some respects, smooth out the demand and optimize the use of the network at the distribution level. So I'll not go into that list in any further detail, but the point is, in terms of the architecture and the components, I think this poses another set of challenges, and I have to say this is an area where I've done a little bit of work before in terms of critical infrastructure dependencies, but I'm just not convinced that the distribution companies have yet really understood in terms of implementing the smart grid, what they are implementing or what they will be implementing in terms of a complex system. They're used to a fairly simple, fairly predictable electricity network. What will be getting introduced is a much more complex electricity network, but actually with an ICT network overlaid over the top. And again, distribution companies being electrical engineers in terms of the operations people, they understand what it takes to keep the network safe, to keep the lights on, and to plan for a network that will satisfy demand. And they understand about failure in terms of electrical components, but do they understand about the issues, potential issues around failure in terms of this ICT network that will be sitting over the top? And I have to say, I think there's a bit of a leap that has to be taken by the network companies. They may not agree with me. I don't know if any of them are here to refute that remark, but I think there is a big leap that actually has to be taken there in terms of understanding what this smart grid actually is, understanding how complex it is, understanding the interdependencies between the various components of that grid. What happens when it fails? How do we model do we model it in terms of failures? How do we build an understanding of how the system will recover from failures? And finally there, how do we know that it's going to perform? So I think these are all huge challenges in this area. I put a few slides up on this project IRIS, which I don't know if any of you would be aware of. It's an EU framework FP6 project, which is now complete. I was involved in it as an expert reviewer on behalf of the Commission, so I wasn't one of the stakeholders or one of the consortium members delivering the project. But it did some interesting stuff. This is an overview of the whole project. I'm not going to focus on this area. This was about developing some middleware, some technology to allow organisations who run critical infrastructure to talk to each other and compare information about risks. That's not so relevant to this discussion. But I think this part particularly is part of the project was all about building an understanding of LCCI's, large complex critical infrastructures. And it looked at the various analysis methods, the various modelling methods in terms of interdependency modelling and so on. And there's obviously a lot of maths in there. It was a 3-year project. A couple of examples of some of the things that they did. They looked at the interaction between the power network and the telecoms network. It's a well-known interdependency that the power network depends on the telecoms network in terms of transmitting data from points in the network, points in the electricity network, back to control centres. And also the telecoms network is dependent on the power network to some degree because the telecoms network needs to be powered. So there's an interdependency there, and what this project looked at, one of the things that the project looked at was, for example, in Italy, looking at the transmission topology. Of course, this is just transmission, 380 kV in this case. And the red, I don't know how well you can see that there, but the red lines on the map there indicate the topology of the transmission grid. They then looked at the topology of the telecoms grid, as it were, and this is the national backbone network in Italy. And they mapped one onto the other, and they also put some demographic data in there about urban areas, etc., etc. And they did some analysis at that level. They also did some analysis at very localized levels in distribution networks as well, looking at the relationship, the interdependencies between the distribution network, a very small part of it, with the telecoms that served it. But some of the outcomes, or some of the areas in that project that are maybe worthy of note, as I've already mentioned, there, the modelling and the analysis, and in fact they ran some simulations as well. They were either done at a national level in the case here, or that they were done on very small parts of distribution networks. And I think the question there is, how scalable is that? If we are now talking about implementing the smart grid across the nation as a whole, then we need to be able to model on a much wider scale than this project did. So I think there's plenty of work needing done in that area. Also, not being a modelling expert, this was something which I didn't really fully get to grips with, but essentially there were many different modelling techniques that were introduced and used throughout this project, and part of the objective, I think, was to try and bring those together, either unify them in some way or couple them in some way. And I think if you look at the IRIS website, you could perhaps draw your own conclusions, but I didn't come away thinking, yes, they've done it. So I think there's a lot of work potentially that could be done there. And of course, the other point worthy of note is, although they gave a nod to what they called next generation networks, it was very much focused on the current architecture of large complex critical infrastructures. So based on the traditional type of network, and didn't really focus on how we might do this in the future when we have smart grids. And just for information, I'll not go through that. The participants in the project are listed up there. I think you're all going to get copies of the slides, so you'll see that. Just in terms of a couple of examples of where complexity has resulted in some real-world problems. Telecom New Zealand, they launched their new mobile phone network late last year. It seems to, as far as recently as April this year, they had 4 major crashes and lots of disruptions throughout this new network that they had implemented. The CTO has been sacked. The network's still not reliable, and there are unidentified software issues remaining. I don't know where this quote came from. One of my colleagues had put this slide together, but someone from Telecom New Zealand has obviously made this statement: there is nothing fundamentally wrong. Well, I'm sorry, but a network that isn't working is fundamentally wrong. I think the key point there is that obviously we're looking at examples which perhaps could have some relevance to smart grids. It would appear that there have been failures in planning and design and diagnostics and actually managing the operation of the network, as well as the fact that if the word software creeping in there, software reliability comes to mind as well as being an issue. But here's a real example of a major implementation of a network, and it didn't go too well. Just a brief mention of the sort of complexity challenges that we're seeing in other sectors as well. This is from the Sir Henry Royce lecture this year on smarter transport. Apologies for the Jamie Houghton from IBM making comments about the number of sensors that exist or will exist in the future. The fact that we now have a multiplicity or will have a multiplicity of interconnected systems. We have systems of systems, and we need to be able to collect data. We need to turn it into useful information. We need to be able to react in real time, potentially, or near real time. And the comment that he made was, at the moment, it takes too long to convert that data to information for use in real time. So they've got the data, but the system isn't able to support real-time decisions. So again, the relevance for smart grids is, we might have some theories which work at a theoretical level, but can we actually implement them? Can we implement them at the scale that we need to implement them? And can we actually get the kind of response and performance that we need out of the smart grid? A couple of final slides. What am I doing for time? Okay. All right. Okay, that's no problem. I think I've only got two more slides anyway. So what's being done now? Again, this is focused on the distribution network operators. Ofgem's price control, Ofgem being the regulator for the electricity and gas markets in Great Britain. Ofgem, within the regulatory regime for the distribution network operators, the price control as we call it, they have allowed, or they put aside a £500 million fund called the Low Carbon Network Fund, LCNF, and they have invited the distribution companies to bid for money from that fund. And what they want the distribution companies to bid for or propose are projects which will prove smart grid technologies, both at the kind of individual technology level, but also at the multiple technology and integrated level as well. They want to see new technologies, they want to see new applications of technology, they want to see new operational arrangements. Again, this is the idea of the network operators moving to be more like system operators, and they want to see new commercial arrangements to support all of that. So the distribution network operators are currently very busy preparing these project proposals, and in fact the initial screening submission proposals need to be in, I think, 22nd of June. Most of the network companies that we are aware of are talking to various different partners and pulling together projects which involve vendors of systems and also academia as well, in order to try and put forward compelling project proposals across a whole range of things. Because it's a competitive process, the distribution companies are not talking to each other about it. Surprise, surprise. So there's a lot of activity going on behind closed doors in order to prepare these proposals. As well as LCNF funding, of course the distribution network operators are looking for other sources of funding as well, so they're popping up in FP7 proposals and proposals for other forms of funding as well. At an industry body level, the industry body that represents the distribution companies is called the Energy Networks Association, the ENA, and they have an Energy Networks Futures Group, the ENFG, and essentially what they are doing is representing the common interest of the industry to both Ofgem and government as much as is possible at this stage, because, as I say, there's competitive work going on in the background as well. But the network companies, once they are awarded LCNF funding and they make progress with their projects, they will actually have to disseminate that information amongst each other. And the Energy Networks Futures Group within the ENA is a potential route for doing that. So there's a lot of activity going on within the industry, but it's early days yet. I should say that this Low Carbon Network Fund, this is the first round. So it will be interesting to see what kind of projects are going to be put forward. There is no history, if you like. But when we come to next year for the second year of funding, obviously we will know what the first year funding allocation was and what the projects were, and that will start to inform what looks like being good projects for year 2 and beyond. So a very quick summary. Smart grids are introducing significantly, or will introduce significant complexity to the distribution networks. It will make control and it will make decision making very, very complex. It's a large scale problem. You know, we're moving to a world where everything is less predictable. There are going to be multiple options, there are going to be multiple parties involved, and we've got to be able to optimize that. And we've got this idea of what I've called here distributed and centralized control, the hierarchical idea that I was talking about earlier on. In terms of the actual complexity of the architecture, we must remember, of course, that this is a combination of both a very complex power system and a very complex ICT infrastructure. And one of the phrases I've been using for some of my distribution network company colleagues is saying, well, in the smart grid, the smart part of the smart grid needs to be as dependable as the grid part of the smart grid. They understand the grid part, but they don't understand the smart part yet. The interdependencies, as I say, are not well understood, and there's this whole concept that we don't really know how dependable this system of systems is actually going to be at the end of the day. Okay, that's me. Thank you very much for listening.
So I'm conscious we're a little bit over time and we've got a shorter lunch break today with needing to set up the seminar room. So one quick clarification question.
There's a lot of hype. Fascinating presentation. Thank you very much. There's a lot of hype, of course, surrounding smart grids. I've been involved in a number of those projects and evaluated some of them. And quite surprisingly, when looking at the value of the smart grids, I saw some numbers comparing net present value of the smart grid with respect to constraint management and distribution networks against good old new cables.
Yes.
Being put into the network, and the NPV values were actually quite similar.
Mm-hmm.
So basically, of course, the difference is that either you invest upfront and or spread around over those years, and with the 5-year price review period, it's better to spread it. But investing into infrastructure has better criticality, it's more dependable.
Yes.
So could you comment on that, on the value of smart grids?
I think it's an open question. I agree with you that it's not clear. Let's put it in simple terms. It's not clear that the business case for smart grids is good enough. You can look at lots of different analysis, some of which comes out positive, some of which comes out marginal, some of which comes out negative. Take your pick. So I can't really answer the question, but I do agree that there's a lot of uncertainty. One of the recent reports that I saw, it was related to, it was an ENA report, which I'm sure I can point you towards later. But the impression that it gives you is that smart grids have a greater benefit for less penetration of this new stuff. So if we've got 10% EVs, electric vehicles, smart grids actually have more of a benefit than if we've got 100% penetration of electric vehicles. So there's some graphs which I can show you from that report, which provides some interesting reading. But what it points to is that in the shorter term, the investment in smart grid is more sensible, but in the longer term, it's not so clear that the investment in smart grid is so sensible.
We need to finish the session and start lunch. One quick request from the facilitators of the breakout sessions: could we have an initial show of hands as to how many will be in each session? You're not committing yourself to anything; it's just for our preparation. So, a show of hands for the economic projection modelling presented by